Hello all, this is Jordan Collins for CSCI 3423. This is my final project implementation for the Kindergarten Business Database. Information is the currency of the 21st century. Until the computer revolution, we stored this information rather haphazardly in the tombs of dusty archives and ancient libraries. As the ages progress, however, we have developed complex mechanisms for storing and connecting information together. Our most recent and modern method of storing information is the relational database system. The information age could not exist without the use of these systems, which range from tiny personal databases to massive server farms in the California hills, housing the personal information of billions of individuals across the world. Businesses especially have benefited from the large-scale design and implementation of relational database systems. These systems allow every part of an organization to function like a well-oiled machine, connecting disparate units of data together using the power of the modern computer. Long gone are the days of filing cabinets and armies of workers piecing hard copy data together in order to operate a business. This project seeks to design and implement a database for this very reason, to organize and successfully run a school for kindergarten-aged individuals. This project seeks to organize datasets related to the normal operation parameters of running a school, allowing the employees the ability to quickly gather and report on all aspects of the school's function. By keeping detailed records on aspects such as student information like health, grades, along with administrative data such as inventory and staff information, this database will alleviate the time-consuming pressures associated with good record keeping and operational procedures. Furthermore, this project seeks to build a database which allows the rapid communication between the operational employees and the students and parents they serve. Right, so part 2, database description. This project is a relational database that contains 6 tables, ranging from student information to inventory information. The first table contains student data, with columns for student ID, first name, last name, date of birth, parental ID, and medical notes, such as the allergies and chronic conditions of the students. The second table contains columns for family data, such as parental ID, father's first and last name, mother's first and last name, and father's phone number, mother's phone number, and of course, email address and home address. The third table contains columns for grade data, such as grade ID, student ID, class ID, the date of assessment, and, of course, the grade. Often, kindergarteners are graded on a simple scale, such as D for developing, E for expanding, S for satisfactory, and N for needs improvement. We use this scale for the data housed in our grade table. The fourth table contains columns related to classroom information, such as class ID, class subject, such as simple math or language arts, etc., teacher ID, and class time. Table 5, on the other hand, contains faculty information, such as the faculty ID number, first name, last name, phone number, email address, and home address. The sixth and final table contains information about inventory, such as the product ID, faculty ID, product name, location ID, and quantity. Data stored in this database encompasses data types ranging from integers, characters, and various characters to MySQL-specific time and date data types. Additionally, this system will rely heavily on DBMS-generated numeric counters to keep track of a variety of primary keys. All right, next up is our data model and design. So first we have our theoretical entity relationship diagram, which was designed after the proposal stage of this project. As you can see, we have the 6 tables mentioned earlier and various weak and strong relationships between them. The relationships visible here are typically between the DBMS auto-incremental columns in each table, so our primary and foreign keys. The most obvious relationship is between the family table and the pupil table, where family ID and family directly relates to pupil ID and pupil. Pupil ID and pupil also relates to the grade table, which houses a foreign key for pupil ID. The grade table is slightly more complex, with foreign key, class ID, relating to the primary key of the class table. Furthermore, the class ID foreign key in the grade table forms a relationship with the class table via the class ID column. The class table is by far the most complex relationship-wise. Class ID is the primary key, but the teacher ID column contains a strong direct relationship to the staff ID column in the staff table. The class ID in the class table also functions as a foreign key in the location ID in the inventory table, where it helps us keep track of the classroom locations of each inventory item. Finally, the staff ID, the primary key for the staff table, is also present in the inventory table as a foreign key, which tells us which teacher is in possession of which inventory item. All right, and then I also went ahead and did the MySQL reverse engineered ER diagram. As you can see, it's identical to our theoretical one. All right, and so for the second part of the data design, we're going to do the data dictionary. And this is going to include everything for every table we have. So family, pupil, staff, class, grade, and inventory. All right, first up is the family table. So first we have our primary key, our family ID, data type integer, and our restrictions for this one are not null and auto increment. So we have the DBMS auto generating numbers for our column. And of course, this is a unique family identifier. Next, we have father's first and father's last name, and data types for these are character 25. And our restrictions are null, just like our mother first name, mother last name, which have the same data type. These are all null, and the reason for that is we might have families that don't have, they might not have a father, they might not have a mother, or it might be mixed like that. Next, of course, we have father phone and mother phone, character 12 for data type. And these are null as well in case we don't have those available. Next, we have our primary email. So this is a various character set to 100. And for email, it's not null unique. So you have to have one, but it has to be unique. And home address is similar, various characters, 100, not null, so you have to have an address. Okay, next up is the pupil table. So we got the primary key, pupil ID, integer type, not null, auto incremental, just like the first family ID. So we've got that, and then we have pupil first name, pupil last name, and those are the same characters set to 35, not null. You got to have a student first and last name. Next up, you have the pupil date of birth. This is specifically the date data type, which is specific to MySQL in this case, and you got to have one. So the student date of birth is measured in year, or YYYY / month / day. And okay, next we have pupil medical, and the data type for this one is text. It is null, so you don't have to enter anything for there, and it'll appear as null. But for text data types, you can enter pretty much paragraphs if you need to. So this is going to relate to any student medical notes you might need to add. Okay, and finally, we have our foreign key, which is family ID, integers, the same as our family ID in the family table. It's not null. You have to have one of these to relate students to their families. And this references the family ID in the family table, of course. Okay, third is the staff table. And first we have the staff ID, which is our primary key. Integer type, our data type is integer. Restrictions, not null, auto increment again. Of course, we've got the staff first name, staff last name, staff phone, staff email. And again, this is various characters, not null unique. And of course, we have the staff address. So their home address, various characters, and they have to have that. Okay, next is the class table. Class ID is, of course, primary key, data type integer. We've got the same for restrictions. Next, you have class subject, which data type is character 25. You have to have a class subject for this. So, for example, our class subject would simply be math or math 1, depending on what it is. All right, now we have our foreign key, and this is our teacher ID. So this will relate the teacher to the class they are teaching. Can't be null, of course, and this references staff ID in the staff table. And last but not least, we have class time, which is our data type for that is time in MySQL language. And so that's counted in, you've got hours, minutes, and seconds. All right, the fifth table is our grade table, the more complex one. So first we've got our primary key, which is assessment ID, integer, same as before for restrictions. Next we have two foreign keys. So we've got our pupil ID, which references pupil ID in the pupil table. And then we have our class ID, which is another foreign key that references class ID in our class table. And to end it, we have our assessment date. So the date the date the assessment was administered, of course. And then we have our grade column, which is character set to 10, not null, and mentioned before, S is satisfactory, D is developing, E is expanding, and N is not developing. Right, last but not least, we have our inventory table, and our primary key is product ID, data type mixture, same as before. Foreign key, however, is the staff ID, which references staff ID and staff. Then we have product name, character set to 35, and this is simply the name of the inventory product, so like crayons or coloring book. And next we have our foreign key, another foreign key, which is location ID, which references class ID in the class table. So they have different names, but they're the same. They're the same. And last, we have quantity, integer, not null, and this is simply the quantity of inventory item that we possess. All right, next up is our limitations of design. So there are a few inherent limitations to the design of this database. While the structure is sound, consolidated to normalization form 3NF, some of the columns lack the ability to account for certain case-specific anomalies in user data. The family table, in particular, possesses some detail-oriented problems. For example, the family table structure only accounts for traditional nuclear family scenarios. The limitation of the column design excludes the ability to enter data for step-parents, same-sex couples, and legal guardians who have enrolled their children in this kindergarten. So i.e. one father, one mother, one stepmother, or just two fathers. Additionally, in the case of co-parenting from divorced families, it only contains space for one email address and one home address. It's entirely possible that students may have two permanent addresses in this scenario. Moreover, the design of this database may be rather challenging to maintain and update. The multiple uses of auto-incremental numbers increases the likelihood of user-submitted error. For instance, it may require careful determination and focus to maintain consistency between family data, student data, and assignment data when updating these tables. In order to offset this difficulty, a well-designed database application will need to be implemented to facilitate user-submitted data. Ultimately, this database schema is lacking a few critical tables related to complete operation of a kindergarten school system. A finances table, for example, which tracks student tuition, inventory costs, and employee salary, would further bolster the use of this database in a real-world scenario. Additionally, it would prove invaluable to establish an entire table related to student medical and health records, where allergies, conditions, shot administration records, and other pertinent health information could be stored independently from the student table. As the schema stands, however, it would be impossible to implement such a design in 3NF without separating pupil medical into its own sovereign table. All right, so next we have the database implementation. So the database has been successfully created. Each table contains 20 rows of sample data to demonstrate functionality. We will suitably validate functionality by demonstrating effective SQL queries. First, we will use two trivial queries that utilize select statements and ordering statements. Next, we will use queries of medium difficulty. These queries will still use grouping, but may also contain composite conditions for selection, computations, or the aggregate functions built into MySQL. Finally, we will use queries that use both subqueries and joins, as well as demonstrating the use of SQL views and unions. Right, first up, we have query number 1. This query will use SQL select statements to gather information from the columns for pupil first name, pupil last name, and pupil medical documentation. All these columns will be taken from the pupil table and ordered alphabetically by each pupil's name. And as you can see, we have the results here. If they don't have anything for pupil medical, it comes out as null. All right, so the second query This is similar to the first. We are taking information from the table family, selecting the columns of information for mother's first and last name and the mother's phone number. And finally, we're ordering the query alphabetically using the mother's first name. And as you can see for this first one, this is Theodore Jenkins, and his mother is not in the database. He only has a father, so if we did this for father, his name or his father's information would show up. Okay, this is our third query. In this query, we're using a select statement, which returns all column values that meet our where criteria. We are taking these column values from the inventory table and grouping them by classroom location in ascending order. Our where statement specifies that we only want to return the columns for inventory supply whose quantity is greater than or equal to 25, or less than or equal to 100. And as you can see, we've got all of them. It left a few out that didn't meet our where criteria. All right. Our fourth query is a query that uses the SQL expressions built into MySQL Workbench. We are using the grade table, selecting the grade column, counting every recorded instance of a grade using the count asterisk function, and calling it number of S grades. We can achieve this by using the group by command and specifying only S or satisfactory grades using the having command. So you can see it's right here, and it returns 19 S grades for all the students. All right, so we're on to query number 5. Here we're using a subquery to combine the staff and class tables into a single readable table. So these are like temporary tables, essentially. So using staff ID, which links to our teacher ID as a key, we are selecting for employee's first and last name from the staff table, using a subquery to link it to the class table, and searching for the first and last names of the staff that teach one of the 4 reading classes. As you can see right there, we've got a like statement, so like reading. So we'll come up with all of the different reading classes, and these are names. All right, on to query number 6. Much like the last query, we're using a subquery to search the information contained in 2 separate tables. In this query, however, we're searching for the father's first and last name, his phone number, and the primary email address of his family using the family table. We combine the 2 tables using family ID as a common key, using a subquery to search the pupil table for a student named Theodore Jenkins, and returning to us the information on his father. So you can see it's all there. You got the subquery and first name, last name. And as you can see, here's Keith Jenkins. All right, for query number 7, we're going to use an inner join to link the pupil, grade, and class tables together in one readable format. So we select for student first and last name, class subject, and their corresponding grade. Next, we use our foreign key constraints for pupil ID to link the pupil and grade tables together, and then use class ID to link the grade and class tables together. You can see that up here. And finally, we order by the student's last name to generate our results. And as you can see, it's right here. We didn't use unique, so it's going to come up with every, the student's first and last name, and the subject and the grade they got. Pretty helpful. All right, for query number 8, we're going to use a left join to combine 2 tables together. Left joins are useful to show null values from the outer left table. So in our example, we organize the staff table and the inventory tables together, searching for employee first and last names and using a left outer join to find out which employees have supplies and how much they have, and which employees don't have any supplies at all. So ordering the results eventually based on staff last name. So you can see here, it shows up with quantities that don't exist, so null values for those. Okay, and for query number 9, we're going to use a right join for the tables family and pupil. And a right join is specifically useful if we wish to return rows on the right table that do not have values for one of our select statements. So Theodore Jenkins only has a father listed in his family table, but we want to include him in the results. So it'll just show right here that he doesn't have mother's phone contact and stuff like that. Okay, and query number 10. So this one uses an inner join, like our previous examples. However, here we include the creation of a view. So views in the terms of database software are query generated tables that can be saved and called upon later. We call views by selecting the columns we want right here, and then use the name of the view and a from command to generate results. So from the emergency contact we create up here, and you get all the information. So this can be helpful, especially if you're trying to contact someone who has an allergic reaction, for example. Okay, next we're going on to query number 11. So in this SQL query, we're going to create another view using the create view command and call upon it by using a select and from command to return its value. But instead of using an inner join, we're going to use a subquery. And this is similar to query number 5 that we did earlier, but we will be searching for math teachers instead of reading teachers. So same except with math and selecting all the columns for math teachers. And here's all the math teachers. All right. And last but not least, we have query number 12. So in this case, a union operator that we're using right here is used to combine the results of multiple select statements from two separate tables. Here we are combining the staff first and last names from the staff table with class subject and class time from the class table. And the result is a single combined table that shows results from both select statements. So you've got the first select statements up here, and then from class subject and class time down here. Okay, that is it for my presentation.